Students, let us talk about the equation of continuity in case of flow of a fluid. Okay, so let us consider a tube of non-uniform cross section. Non-uniform cross section means you see the cross section is so low, and at B it is very high. Okay, comparatively. So and we are considering that there is a liquid and it is flowing with flowing through this tube from A to B. Fine. And I will consider that the cross section here means the whole cross section is A1 and this whole cross section here is A2. Fine. And the liquid that is flowing through it is first of all, as we have already mentioned, in all the cases we will always consider a liquid which is incompressible. Okay, and its viscosity is also means zero viscosity. So that thing, zero viscosity, or you can say that it is called non-viscous. Okay, so let us consider that incompressible and a non-viscous fluid is flowing through this tube from A to B. Fine. And for our convenience, what we will consider, this is the axis of the tube. Okay, and we will consider a very small infinitesimal tube inside it, parallel to the original tube. It's an imaginary thing. Okay, don't think that I have considered another tube. It's an imagination, and this small area is again now dA1 and this small area is dA2. Okay, and suppose that in time t, okay, so in time, sorry, I will consider, let us consider that in time dt the liquid flows through a distance ds1 at A and ds2 at B. Okay, because suppose this molecule reaches here, so in time dt it covers a distance of ds1, and here at time dt it covers a distance of ds2. That's all we have considered. Now suppose that now if I ask you what is the mass of fluid, okay, entering the infinitesimal tube, okay, at A with cross section dA1 equal to, see, the whole section is A1, but this whole small infinitesimal tube has a cross section of dA1. So dA1 is the area of cross section, and in time t it travels, suppose this much distance. Okay, that distance I told you that this distance is nothing but ds1. Okay, so ds1 and dA1, so this is the ds1 distance into area. This is the volume. You know that mass is what? Volume into density. Sorry, density, because density is mass per volume. So mass equal to volume into density. So this is the volume. Okay, volume of liquid entering this cross section in time t. Okay, so mass of fluid entering the infinitesimal tube at time at A with cross section d1 in time t. Okay, so this is a volume into what density, so I will name it as rho. Okay, let me name it as rho1. At t density is rho1. So therefore mass of fluid, okay, entering the infinitesimal tube with cross section dA1 at A per second. Sorry. per second is equal to. Okay, so see this is entered in time dt, isn't it? So this is time dt, okay, not t. Fine, so it will be ds1 dA1 by rho by dt. Fine, but you see this thing, ds by dt, distance divided by time, that is nothing but what? Velocity of flow of the liquid. Okay, so velocity of the flow of liquid at what? At this cross section. So let me name it as v1 dA1 rho, so rho 1. Understood? So where v1 is the velocity of flow of fluid at A. Till now we have considered what is the mass of fluid entering the infinitesimal tube at A at cross section D. Okay, and now if I do the same, now you know that this mass is entering here, now similar mass is leaving here also. So if I write down mass of fluid leaving, okay, the infinitesimal tube with cross section dA2, because here it is dA2 at B in time dt is equal to, okay, again mass means again volume into density. Volume means here again you see what was the thing, that in time dt the volume will travel a distance of how much? ds2. Okay, and what is the area of cross section? dA2. Fine, so it will be dA2 into ds2, that is the volume. Understood? And density what? Rho 2. Suppose the density here is rho 2. So therefore mass, similarly I will not write whole of this thing again. So mass of fluid leaving the infinitesimal tube with cross section d2 at b per second. So all this thing per second is equal to what? dA2 ds2 rho 2 by dt. So ds to dt is nothing but what? Velocity. Distance divided by time is nothing but velocity. So this is the velocity of flow of the fluid at the point B. So I will name it as v2 dA2 rho 2. So let it be 1 and let it be 2. Okay, so where v2 is the velocity of flow at B. Okay, now you need to be careful about one thing, that we are considering the same liquid. Okay, same liquid means the density is not going to change from here to here, so there is no use of considering rho 1 and rho 2. So what one point is what? Rho 1 is equal to rho 2, because it's the same liquid. Okay, and there is another thing. Tell me, when the liquid is going from here to here, okay, is there anything any leakage in between? No leakage. Is there any additional tube from which water or fluid is coming inside? No, there is. That means there is no sink. Sink means nothing is taking out the liquid, no leakage, and there is no source, means we have not connected any extra tube in between these 2 points to add to the fluid, nothing. So that means whatever is coming inside in time dt should go out in time dt. Okay, in the similar same time, isn't it? Because you can from the law of conservation of matter. Okay, so if you want to conserve the law of if you want to conserve the law conserve the matter of the particular fluid that is flowing through it, what is the situation? That mass of the fluid that is entering the whole cross section at the pipe A should be equal to the mass of the fluid that is entering the whole cross section of the pipe B. That should be done. Now this thing that we have calculated, this is the mass of the fluid, not through the whole cross section, only through dA1, and this is the mass of the fluid that is passing out, but this is not through the whole cross section, but this is through only dA2. So we have got to know that mass of the fluid entering dA1 at A per second is V1 dA1 rho 1, okay, and mass of the fluid leaving dA2 at B per second is V2 dA2 rho 2, and already we have discussed that we are having the same fluid, isn't it? So rho 1 is equal to rho 2, so there is no use of considering rho 1 rho 2, so it is simply rho, okay, and here also it is simply rho, okay. Now if I want to, this is for dA1, okay, and this is for dA2. As you remember the figure, so it is like this, isn't it? So it is B, this is A, this is A1, this is A2, and we had a very small infinitesimal tube in between going like this, and it was having dA2, and this it was having dA1, okay. So now if I want to get it for the whole tube, as we discussed that according to law of conservation of matter, the fluid entering is the whole cross section of A in a particular interval of time should be equal to the fluid in leaving this whole cross section of B. Fine. So what we are going to do, so I need, this is for dA1, so I will have to integrate whole of this to get for A1. Similarly, this is for dA2, I will have to integrate this for getting whole for A1. So therefore what I will write, therefore total mass of fluid entering whole cross section A1 is equal to, I will do integration, so it will be V1 dA1 rho. So rho is a constant thing, isn't it? So rho is not going to change, and V1 I am taking out, so it is dA1, okay. So it will go from 0 to A1, so it is simply rho, this is rho V1 A1. Similarly here also what will happen, total mass of fluid leaving the whole cross section A2, this is also per second, this is also per second, okay, because this is per second, this is also per second, so it is equal to, again integration, V2 dA2 rho 0 to A2, V2 and rho coming out, 0 to A2 dA2, so it will be A2 V2 rho. Okay. So according to what is that, according to law of conservation of, so according to law of conservation of matter, what is this thing, total mass of fluid entering the whole cross section at A1 per second should be exactly equal to total mass of fluid leaving the whole cross section A2 per second. Okay, so what is the statement? Rho V1 A1 is equal to rho V2 A2. Okay, so rho gets cancelled, what remains, V1 A1 equal to V2. Okay, so that is the statement for continuity equation. Okay, so if you remember, product of area of cross section and velocity velocity of flow is nothing but rate of flow. Okay, so what we can write in return, that rate of flow at A is equal to rate of flow at B. So that is the total statement of continuity equation for a fluid motion.